Welcome to part 2 of this video series here. In this video, we're going to be wanting to plot out and visualize what is going on with the changing mole fractions in both the liquid phase and in the vapor phase, if we're dealing with a constant temperature, as well as if we're dealing with a constant pressure, and be able to see what is the behavior like for a binary compound of benzene and toluene. And we've already done the first part of this, which is be able to use or write out Python functions to calculate the dew temperature and pressure and the bubble temperature and pressure. And so we're going to then move forward into our second section here, which is we want to generate plots of this binary vapor liquid equilibrium phase diagram, and then we're going to be using the constant temperatures of 393.15 Kelvin and 150,000 pascals. So let's dive in and write out our plots that we're going to be interacting with. So we have two plots. One is with a constant temperature of 120 degrees Celsius or 393.15 Kelvin. And in this other plot, we have a given pressure that stays constant at 150,000 pascals. Starting with the first plot where we have a constant temperature, let's figure out our axes here. So in our x-axis is going to be dealing with our more volatile component. So we're going to be graphing out benzene as our x1 in the liquid phase and as y1 in the vapor phase. And then, because we're dealing with a constant temperature, we have pressure in the left diagram and temperature in the right diagram. Now, let's think a little bit about what we're going to do here. So we want to have our, conceptually looking at the liquid phase in the upper part of the diagram and the vapor phase in the lower part of the diagram. And if we think about it for the pressure, when the pressure increases, the vapor is condensing and from the increased pressure. And as it condenses, it becomes the liquid phase. And so we need to have our liquid at the higher pressure points of our graph. And if we have 0 mole fraction of benzene all the way up to 100% mole fraction of benzene, then what that means is when benzene is at 0, part of the mole fraction, either when it's in the liquid or vapor phase, that means we have 100% pure component of toluene, which is a less volatile compound than benzene is. And if toluene is a less volatile compound, what that means is that less particles are going to be breaking free from the surface or re-entering the surface, but less are going to be breaking free from a surface at its pure component vapor pressure, which means that it's going to be at a lower vapor pressure. And so, because if less vapor particles are breaking free, that means there's less vapor pressure being imposed on the entire system by the vapor. So if we're at 100% toluene, then that means the vapor pressure is going to be lower. And then all the way over here, if we're at 100% benzene, then it's the vice versa. The more volatile component means that we're going to have a higher vapor pressure. And so we should be anticipating that our graph should go from low to high. And what we're communicating with this right here is our bubble pressure. Because what we're saying is at our given temperature, what does the pressure need to be when the first bubble forms, when the first vapor forms from 100% liquid? And what we're going to be doing is to think about this over here is if we have our X1, so that's our benzene, and we have our toluene, and we start out at 0, move all the way to 0.1 to 2, all the way down to 100% of the mole fraction there, then that means it's the inverse for our benzene. And if that's the case, then what we're saying here is that at a given temperature, our pure component vapor pressure for each component is going to be fixed based off the current temperature, based off of the Antoine equation and the parameters that are set for that for each respective temperature. And so when the mole fraction is a certain amount, for example, when there's a 0 amount here, that gets multiplied by our pure component vapor pressure by Raoult's law, and then that will then show what our partial pressure is from benzene. And then the same thing with toluene. And then, as we saw, the bubble pressure is just the sum of the partial pressures, and so it's going to be this plus this. And so let's go ahead and move forward now with writing this out on Python so that we can visualize what this graph is going to look like. Going over to our Python code that we've been developing, we are going to need to start by adding in our plotting tools in order to show our plotting functions and our plots. So we will plotly.subplots. Now this is board, we're just this is just for templating purposes right here, so that way we can have our our plots as just dark for a dark background. Now we need to think about everything we were talking about here. So what we're doing is we're just wanting to be able to graph out the sum of the partial pressures, because we're going to start with what happens if we have our constant temperature at 120 degrees Celsius, and which is 393.15 degrees Kelvin. And so then what is the bubble pressure going to be at each respective mole fraction between benzene and toluene? So that's what we're going to move forward with our code. And X1 and Y1 are just expressing both just the mole fractions, but the phase is the only thing that's different. So the liquid versus the vapor phase for each substance. And so we can actually just communicate that simultaneously through a third variable and just call it Z, because Z is going to be able to say, at Z, it's going to be able to cover both our X1 and our Y1 at each mole fraction. So we're going to go ahead and plot that out. So Z1, and what we are going to do is plot from 0 mole fraction all the way to 1, and we'll do 11 points for it. Now our Z2, all that is 1 minus Z1. And then our temperature, which is being held constant at 120 degrees, let's move this down. Let's delete that from up here. Move this down to here, just to express our temperature is being held constant. And so we're going to be plotting out our, let's see, so our bubble pressure list, because we're going to call it list because we can't just call it bubble pressure because we already have a function defined as bubble pressure. And so our bubble pressure list is going to be our Z1 value multiplied by the pure component vapor pressure of that substance, because that is Reule's law. That's going to then be, our mole fraction in either phase, our mole fraction, for the liquid phase multiplied by the pure component vapor pressure is going to be our partial pressure for that respective component. And so that's what we're going to be doing for our bubble pressure. And so in order to multiply it by the pure component vapor pressure, let's go ahead and call it by a variable. And that variable is going to be whatever the pure component vapor pressure is for each respective temperature. And so we'll say by PSAT. Now for benzene first, and then toluene second. So all we're doing right now is using Reule's law. And now we're going to go ahead and graph this out. Where we have we're going to have rows equals 1, columns equals 2, and then our x-axis is going to be our Z1, our y-axis, because we're dealing with a more volatile substance for x-axis, our y-axis is going to be our bubble pressure list, and we're going to go ahead and put that in row 1, column 1, and then let's see how that doesn't like the amount of parentheses I have. Okay, so what this is showing us here is what we have graphed out and anticipated right here, which is our bubble pressure line. And so that should be escalating as we discussed previously, because here when it's pure component of toluene, 100% toluene, the vapor pressure should be lower. And as it progressively increases to being more and more toluene, here we see the pressure points varying at each point here. What we see is our pressure does indeed increase, which we would expect, because when we have 100% of benzene, our vapor pressure should be higher, as it being the more volatile substance. Let's throw on some labels. And we need to say that our x-axis is, let's go ahead and NP space from 0 all the way to, from 0 to 1 with 11, and the title we'll call this our x1, y1, and then we'll update our y-axis just to better visualize this, and this is going to be and this should be in our row 1, column 1. Yes, we want that to be our row 1, column 1. So we'll say title equals pressure in pascals, and row 1, column 1, and then wait a second, that needs to be tick values. And then let's go ahead and give our overarching layout its name of what we're going to be doing here. So this is our binary vapor-liquid equilibrium for both benzene and toluene. Didn't like that. Let's close that out there. Here's that. And maybe that doesn't need that there. Okay, there we go. So this is just cleaning things up a little bit so we're having everything properly labeled. Now what we're going to need to do is at our constant, so this graph here is our constant temperature, and this is showing for each point along this line, when will the first bubble form if we're dealing with 100% liquid up here? At what pressure will the first bubble form based on the mole fraction ratio between benzene and toluene? So as we see, it's going to differ, which we would anticipate. It's going to require a higher pressure for the first bubble to show up when we have 100% benzene as our more volatile component than when we're down here when it's 100% toluene. And so that makes sense that our bubble pressure should be changing as the sum of partial pressures will change based off of the amount of mole fraction that we have for each component. And so now what we need to communicate is and add to this is our dew pressure. And so how is our dew pressure going to show up on this line, on this graph, as the mole fractions change between the two compounds? For our dew pressure, let's go back to our graph that we were just working on here. And dew pressure, again, is just when we have our fixed temperature, which we have here on our left graph at 393.15 Kelvin. At a fixed temperature, we're asking at what pressure will the first drop form when we're at 100% vapor here. We're at 100% vapor. At what point, at what pressure will the first drop form from 100% vapor into the liquid phase? And so what we're anticipating again is, right, it's going to climb for the same reasons when we have 0 benzene and 100% of our less volatile substance of toluene. Our pressure should be lower at which the drop should form, and then we'll go ahead and graph this out and see what this looks like in comparison along the same increments of mole fraction changes between the two substances. So going back to our code, to graph this out, we're going to need to make a list here, an array of values for our dew point, which will be, we'll also have to call that list because we already have dew point as a function. So we'll create an array there. And then what we're needing to do is say we're going to need to run a for loop because we're going to have our y values in our dew point and at our fixed temperature, and we want to be able to say for all the values from 0 all the way to 1, what is going to happen in our predefined function that we've already set here for dew pressure. We've already showed as this, and so that's what we're trying to run through with our values. So if we say for y1, for y1 in z1, y2 equals 1 minus y2, not y to y1. And then we're going to need to say, we're going to need to create an array of values. Everything from y1 and y2 is going to equal our y, because when we append our list in our for loop here, we're bringing in our function for due pressure that we've previously established. So for each of our y values, which are going to be going along the for loop there, along the same increments of mole fractions that we saw for our x values, which is the mole fraction in the liquid phase. Now we're doing with the vapor phase. We're going to have our fixed temperature. Let's go ahead and run that. And then we're just needing to add another plot, but we just need to change this to due pressure. And then let's go ahead and name these now that we have two of them. That's our bubble pressure line, and this one is going to be our due pressure line. There we have our due pressure line in red, and as we suspected, it would be climbing just as we saw. So it's not like it was coming from ascending and then going down. It's following the same pattern that we've been discussing with the chemical properties, and going from low to high as we go from the low, less volatile substance all the way to 100% of the more volatile substance. And so now what we're going to do is graph out what do the curves look like when we're dealing with a given pressure, and we're now asking what is the bubble temperature and due temperature. Let's go ahead and shift gears now to talking about our due temperature and our bubble temperature. And that is then when we're given our pressure, at what temperature will either, for due temperature, the first drop form from a composition that's 100% vapor phase, or the bubble temperature in which the first bubble is formed, at what temperature is first bubble formed from 100% liquid. And so going back to our graph here, on the right we have our given temperature at 150,000 pascals, and now instead of it being pressure that is fluctuating, it is the temperature that is going to be changing with that constant given pressure. But as the mole fractions change both in the liquid phase and in the vapor phase, our temperature is going to change, at which points the due temperature and bubble temperature happen. So now we want to consider the fact that with this graph it is flipped. So the volume, or not the volume, but the vapor is going to be on the upper end of the graph, and the reason for that is at a high temperature it is going to be in the vapor phase, and at a lower temperature it's going to be in the liquid phase. And that means that when we consider here that we have our less volatile compound happening there at 100% toluene, when it's 0% benzene in the system, then we are going to end up having our starting point higher. And we want to think about it, it works like this, in the sense that it will require a higher temperature for a less volatile compound to have that liquid vapor liquid equilibrium line is going to be higher for both the due temperature and the bubble temperature to happen. Because it's a less volatile system, it means it's more stable, and it's going to require a higher energy in order for it to change phases to become in equilibrium with each other. And then it's going to descend because as it becomes then more volatile, the roles are reversed. In a more volatile system, it requires less temperature for it already be in between a vapor liquid equilibrium, because it's easier to escape the liquid phase or to re-enter in a more volatile state. And so we should end up seeing something like this, where we'll see our bubble temperature here. And we should see our dew temperature moving like this. And let me go ahead and finish this other graph off that we saw from the function in Python. And this was our dew pressure. Now shifting over to our coding, how do we go about that? Let's set our pressure and our pressure is equal to 150,000 pascals, and then so this is in pascals. Now we have our bubble temperature list, and we're going to make that an open list that we're going to append our values in, just as we have done with our previous dew pressure and bubble pressure. And so we're also going to need our, well, let's go ahead and move forward with our bubble temperature. Yeah, we'll do our bubble temperature and our dew temperature. And so for now, our we're going to go ahead and call it our xy1, and our z1 is already established. So we can do the same for loop because we're continuing to, we already have our z1 set, and it's going to move in those increments from 0 to 1 for the mole fractions between the two compounds. So for xy1 and z1, we can say that our xy2 is just simply 1 minus xy1. And then where we need to consider is that we are wanting to take an array of values from the functions that we've already defined. So we have our bubble T up here, and with our bubble T, what we've already used our root solver, and so as our mole fractions are going to be changing in their composition, moving from less benzene to more benzene, or more toluene to less toluene, whatever direction is going along the increments that we've set, it's going to then end up being a different temperature for each composition within the mixture. So as the ratio between the benzene and the toluene changes, so will the temperature change in which the dew temperature and the bubble temperature happen. And the pressure is going to stay the same at the given pressure, and it's the temperature that's going to be changing at which these things happen. And as it's going, so we want to have if we basically want to append each new value into our list that we've set, because we want to retrack and say, at what temperature do we need to have this, basically our mixture at, that will set our root value back to 0 every time we rerun our analysis of just whatever the composition mixture is currently at. And so let's go ahead and do that now. So our bubble T list, we're going to append. And what is it we're appending? Well, we're taking our bubble T function, and we're taking an array of values within that, as we just walked through and discussed. And we're taking our xy1 and our xy2 values, and we have our given pressure that has remained the same. And then we can do the same thing for our dew temperature. And so for our dew temperature, we've got our list that we're going to append into. And again, have an extra I think I need to put the parentheses right here. Close out that array. There we go. Let's go ahead and run that. And so now we're just going to put those two in our graphs. So we can just copy and paste this here. And now what is changing is our new list that we're doing, which is our bubble T list. And that we're sticking in column 2. And the name for that is bubble T. Do it again now for our dew temperature. Column 2, dew temperature. If all goes well, we should see, there we have it. So as we were predicting here with our bubble temperature descending as it became more volatile, for both our bubble temperature on the bottom and our dew temperature on top, that's indeed what we see happening here with our bubble temperature on the bottom, our dew temperature on top, and descending as it becomes increasingly volatile. Now let's go ahead and name our y-axis for column 2, because this is our fixed, well, we have our fixed pressure, but the y-axis itself is temperature, and that is in kelvins, and that is for column 2. So this video, this part in our 5-part video series, has walked through and graphed the behavior for our bubble pressure, our dew pressure, and then for our bubble temperature and our dew temperature as our mole composition changes from benzene to toluene, from toluene to benzene, for both our vapor and our liquid phases. And this is all, again, according to Raoult's law. Thank you.